Good morning. I'm Heather Mamoni, Membership and Outreach Director at Rubber Division, American Chemical Society. Thank you for joining us at the function and selection of Ester Plasticizers, brought to you by Hallstar and Rubber Division. I'd like to pass it on to Erica Anderson at Hallstar. Thank you.
Good morning, everyone. Thank you so much for joining us. We were very pleased to be giving this webinar presentation, and we hope that you find it educational. Sorry. There we go. So my name is Erica Anderson. I am a senior chemist with the Hallstar company, and I've been with the company for about 4 years now, but I've been in the rubber industry doing everything from rubber synthesis up through compounding, primarily for gaskets and seals applications before this, with a wide variety of elastomers, and then now working primarily with Ester Plasticizers for 4 straight years, but total in the industry about 10 to 12 years. And then we have on another of our chemists, and I'll let her introduce herself.
Thank you, Erica and Heather. Hi, everybody. I'm Dani Lewittes, and I'm a commercial development chemist at Hallstar. I've been with the company for about 8 months now, and this is my entrance into the industry. I do some synthesis work at Hallstar, as well as compounding and testing of our products in elastomers and PVC. So here's a quick roadmap of our presentation. I will first go through some background about our company and familiarize you all with what we do at Hallstar. And then I will give a general overview of what a plasticizer is, going into some of what they do, as well as the science behind how they work. I will also emphasize how Ester plasticizers specifically provide enhancements over other chemistries. Erica will then take over and cover the selection of Ester plasticizers for different formulations and applications, including topics such as compatibility, raw materials, monomerics and polymerics, temperature performance, and structure property relationships. Erica will then show you a few case studies showcasing the problem-solving potential of Ester plasticizers in rubber. So just a quick background on our company. Hallstar is a private yet rapidly growing specialty chemical manufacturer with headquarters in Chicago and R&D centers around the world, including Europe, Asia, and South America. Our main production facility is located in Bedford Park, Illinois. We have over 200 global team members, over 100 total patents, and 6 production facilities. Our core competencies lie in the manufacture of specialty ester plasticizers, with over 100 in our current portfolio. We have extensive knowledge of ester compatibilities by polymer type, which enables us to provide solutions for elastomers, thermoplastics, adhesives, sealants, coatings, and more. Furthermore, we do dry blending of our esters onto silica and calcium. We specifically pride ourselves in the production of phthalate alternatives, permanent reactive plasticizers, and renewable ester chemistries. Our new innovations include esters for increasing surface energy, high and low temperature esters for VMAC VMX, polymeric esters for low polarity polymers, and new bio-based and renewable polyesters. An interesting tool we offer is a design of experiment known as the Paraplex approach, which was designed to optimize the chemical composition of a custom ester plasticizer. As you can see in the surface response diagram on the right, the star pointing to the peak indicates the optimal solution point for application. This useful device can be found on our website and has helped meet many of our customer needs. And this chart just sorts some of our industrial products into chemistries, showing their functions and the corresponding brands that fall into these categories. This is just to give you an idea of the brand names at the core of our business, some of which will show up as examples in today's presentation. In the elastomer market, we serve various applications in automotive, oil and gas drilling seals, print rolls and blankets, conveyor belts, tires, and wire and cable industries. We have a long history in and have developed a lot of knowledge about elastomer modification. So now it's time to get into the world of plasticizers. First of all, what is a plasticizer? ASTM defines a plasticizer as a substance incorporated into a material, usually a plastic or an elastomer, to increase its flexibility, workability, or distensibility. Plasticizers can function as process aids in low loading levels or compound property modifiers in higher loading levels. As process aids, they reduce the viscosity of the mixture for greater ease of processing in the form of lower temperatures and increased flow, as well as lubricating the mixture for cohesion of the uncured compound and reducing adhesion to both mill rolls and molds. Due to the low loading levels, however, they don't significantly alter the properties of the compound. However, as compound property modifiers, plasticizers improve upon various properties such as tensile, hardness and modulus, as well as flexibility, elongation, and tear strength. Furthermore, they enhance flexibility at low temperatures, increase overall temperature range of operation, modify friction, and can even change the physical appearance of the compound. So you may be wondering why we at Hallstar have a keen interest in ester plasticizers. Well, they provide distinct advantages to polymers, such as enhanced low temperature performance via depression of glass transition temperature, and also allow for improved processing and resistance to various fluids. Polymers are generally softer at high temperatures. This is because the polymer, when heated for a prolonged period of time, can break down and create lower molecular weight byproducts that act like plasticizers in the system. However, when heat is removed, the polymer modulus quickly recovers. So drawing off this concept, internal and external plasticization were invented in an attempt to retain the lower modulus of the polymer at lower temperatures. Internal plasticization is not very common, but it does happen during polymer production, in which polymer producers chemically react plasticizers into the polymer chain to control the glass transition temperature of the resulting copolymer products. External plasticization, on the other hand, is much more common, as it's the most convenient and versatile method. This is when plasticizers, typically liquids like oils, solvents, etc., are added during the compounding process. This method allows for infinite ways to change the properties of the polymer. So as you can see in the graphic below, polymers can contain both crystalline or ordered and amorphous or disordered regions, depending on how the chains pack together in space. The compatibility of a plasticizer with a polymer is impacted by the way the plasticizer fits into these regions, and this is what classifies plasticizers as primary or secondary, as you saw in the previous slide. A primary plasticizer can permeate both regions, while a secondary plasticizer can only impact the amorphous region of a polymer. Secondary plasticizers are typically used to dilute primary plasticizers in a formulation. So now we know that plasticizers take up space in different regions of a polymer, but you are probably still wondering how they actually work. Well, there are four main plasticization theories. The first one, the lubricity theory, states that a plasticizer molecule acts as a lubricant between polymer chains. So as a polymer is flexed, the smaller plasticizer molecules glide back and forth between the chains. The second theory is known as the gel theory, which claims that plasticizers break up various gel sites in a polymer, or sites formed by a gel of weak attachments causing polymer stiffness. The third and most widely accepted theory is the free volume theory. This states that plasticizers add more distance or free volume between the polymer chains, which accounts for the lowering of the glass transition temperature of the polymer. The mechanistic theory, the fourth theory, isn't really its own idea, but it kind of fuses and explains the other ones. This theory asserts that since polymers and plasticizers are not bound to one another, the plasticizer continues to move freely from one polymer location to the other, allowing for greater overall flexibility of the system.
So now that Dani's kind of covered how plasticizers work, what their function is out in the world of polymers, how do you choose which plasticizer is the right one for your application? There are hundreds and hundreds of products out there, both ester and other types of plasticizers, and it can be a little overwhelming to try and figure out which is best for your application. There's a number of things to consider when you're looking and narrowing down your choices. The number one thing that is the most important when deciding on your plasticizer is compatibility. If your plasticizer and your polymer are not compatible, the plasticizer will not stay in your polymer and will either bleed out or be extracted out over time, and you will lose any properties that you might have gotten by adding it in the first place. So that is really the biggest thing that needs to be considered before you look at anything else. Moving on from there, you can look at things like processing. Plasticizers many times improve or can reduce mixing time. They can help to lower viscosity of your overall compound for things like extrusion or injection molding. So that's another portion to consider. Of course, just original physicals, your tensile properties of your modulus, your tensile strength, your elongation, all the way down to specific gravity of the compound or the compression set. Plasticizer can have an effect on all of those, and often that's kind of your target that you're working towards. And then depending on your application, you may have requirements for heat aging or just long-term aging of the material and seeing how a plasticizer performs over time, and also resistances to fluids. If your compound is going to be exposed to anything in particular, especially for prolonged periods of time, you need to keep that in mind when you're selecting what type of plasticizer, because the plasticizer can really impact everything here. So it's something, those are all things that you need to think about when deciding. So I'm really going to talk a lot about compatibility because, as I said, that's really the most important thing that needs to be considered, at least at first. If your plasticizer and polymer compatibility is correct, then the materials will form a nice homogeneous mixture during the processing, after they're cured, at their resting temperature, and at the application temperatures, if that's different than room temperature. It's only necessary, though, to have enough compatibility that it will remain in the polymer based on your desired product performance. You probably don't have to worry as much about having perfect homogeneous compatibility if your application is not going to be seeing extreme temperatures or is not going to be exposed to harsh solvents or other fluids that might extract it out. You don't necessarily have to have the exact same polarity between your plasticizer and your polymer to be considered compatible. A lot of other components in your compound could affect your compatibility, so polarity may not necessarily be exactly the same to get good compatibility. And then the numbers given here for loading levels are a little arbitrary, but just to illustrate a little bit, plasticizers could also be used at a lower loading level of, say, 10 parts, but if you increase to 20 parts, you might be pushing past that compatibility threshold and you might start seeing extraction coming out. So loading level is also something to keep in mind when you're looking at compatibility. So as I mentioned on the previous slide, polarity is probably the quickest and easiest way to estimate whether your plasticizer and your polymer will be compatible. The chart that we have over on the right side of the screen here is one of our most famous and widely used pieces of literature, both in the industry and also in-house. I regularly refer to this chart. I have it sitting up on my bulletin board next to my desk right now. It just helps to show relative polarity on the left side of the chart with most common elastomers, with the extremely high polarity materials like nylon or high ACN content NBR, going all the way down to the very low polarity materials like butyl rubber, EPDM, even silicones. And then showing for a relative level, the plasticizer class that kind of coincides with that same polarity. Now, when you're looking at this chart, you don't, as I mentioned before, they don't have to have exactly equal polarity. You know, you don't have to use, say, polyglycol diesters with polycarbonate just because they're on the same line in this chart. You can kind of, though, use it as a guide. You don't want to stray too far up or down that polarity chart because that's when you'll start seeing incompatibilities. Going even further, that's more of a relative kind of qualitative guess while we're looking at these materials. But if you want something to get a little bit more quantitative, you can start looking at Hildebrand solubility parameters. Those are often calculated or tested and published for a lot of common elastomers, and maybe for a plasticizer class, not necessarily a specific plasticizer unless it's a very common commodity material, but you can at least estimate using those numbers. And then going even further, you can get into Small's constants, looking at additive methods of the actual atoms and molecules that are present. Usually, you don't necessarily go that far when trying to decide on a plasticizer. It's a tool that's available, but usually looking at polarity or even solubility parameters is enough to kind of guess at which materials would be the best for your compound, and you can go forward with testing, and usually trial and error is a more effective and efficient way of moving forward than going through and calculating Small's constants, but it is a tool that's available out there. So how do we calculate and look at polarity? First thing that if we look at in an ester, because oxygen and carbon are kind of the two most common atoms that are used in an ester plasticizer, is we look at the carbon to oxygen ratio. There will always be oxygens present. That's what an ester is that group of those two oxygen atoms in the molecule. So by adjusting the number of carbons that we have in the molecule, we can adjust the polarity of the overall molecule. If we increase the carbon to oxygen ratio, shown here with the diundecyl on the left with a very long carbon chain versus the dibutyl on the right with a very short carbon chain, that increases your carbon to oxygen ratio and decreases the overall polarity of the ester. When you decrease polarity, you see a higher oil solubility. Oils are very nonpolar, so as you decrease polarity of your ester, you'll see more solubility in oil. You'll also see a reduced volatility because the ester will always be present. As we decrease polarity, that means we're making the molecule larger, so it's going to be less volatile than a very small molecule like that on the right. Converse to the higher oil solubility, you see reduced water solubility. Water is very polar, so as you decrease polarity, your ester will be less soluble in water. And then you usually see better low temperature flexibility as you decrease your polarity as well. Just to further illustrate how we kind of calculate and estimate, we literally just count the carbons and oxygens present in the molecule and kind of look at that number as a ratio. DBP with very short carbon chains only has 4 carbons present for every 2 oxygens. So we have that 2-to-1 ratio, and that's considered a high polarity material. Going all the way up to the tridecyl with the 13 carbons to every 2 oxygens, you're at a 6.5-to-1. That's a low polarity material with a high carbon to oxygen ratio. This kind of takes a chunk out of that polarity chart that we showed before by putting these plasticizers in order of high to low polarity and showing that they would be compatible with a high polarity, high ACN content NBR versus the low ACN NBR or low polarity NBR. And then just to illustrate with actual data, the changing of the carbon to oxygen ratio, the changing of the polarity, and their compatibility with an oil. The ASTM 901 oil is an extracting oil, so you usually see a weight loss over time after aging in this oil. And with the two first materials with a very high carbon to oxygen ratio, meaning very low polarity, you see an almost 10% weight loss. Whereas with the material on the right, in a very low ratio, so high polarity, you see much less of a volume change, meaning that less has been extracted out because it's less compatible with the oil. So how do we change all of these ratios? What materials can we use to play with that ratio of oxygen and carbon? This is just a piece of the materials that are available out there, but it gives you an idea of the broad availability that we have of materials to play with. From simple monofunctional alcohols, just like ethyl alcohol, up to butoxy, ethoxy with further functionality of oxygens to further adjust that polarity level. And reacting with monobasic acids, just simple propyl alcohols or acids, excuse me, up to benzoic or linoleic and tall oils. And then we also use difunctional materials or glycols for difunctional acids or alcohols. Keep saying that. Ethylene glycols up to hexane diols and dibasic acids from simple propionics up to phthalics or isophthalics. To illustrate some of the most common acids that are currently used, really one of the biggest, most common materials right now is an adipate or adipic acid, as shown here. The phthalates used to be the most common, especially for monomerics, but as more and more governments are starting to regulate those materials, they're becoming less and less common. And one of the most common replacements for phthalic materials is adipates. This is because it's relatively inexpensive compared to a lot of other acids out there, and you usually can get some similar performance materials with adipates versus phthalates, and this is just what it looks like when you're looking at a chemical structure. Acylates are another common material. They're more expensive and they're less polar, as you can see with the longer carbon chain between the acid groups. And glutarates are also different option, slightly less polar, or slightly more polar than the adipates with having that shorter chain. There's the phthalic, as I mentioned before. The reason that phthalics were a little bit more unique was because they had that aromatic ring coming off of the side, but they were very inexpensive, very effective plasticizers. Unfortunately now they're being regulated because of all of the hazards associated with them, so they are much, much less common, but this is what they look like. And finally, the sebacates is a nice long carbon chain, so these tend to be better choices for lower polarity materials, but again, they tend to be a bit more expensive. So what are the effects of using different types of acids? They're usually separated into two basic groups. There's the aliphatics of long, straight carbon chains. So of the materials we just looked at, things like adipates, sebacates, succinates, glutarates, all of these that are just straight carbon chains. Versus the aromatics like a phthalate or a benzoate, a trimellitate. Those are more commonly used now, now that phthalates are moving away, but benzoates and trimellites are still fairly widely used. So why would you use aliphatic versus aromatic? Aliphatics tend to be very efficient at reducing their viscosity, so less material is needed to bring that viscosity down. They tend to have much better low temperature flexibility than aromatics. They also tend to have very good volatility resistance, especially for their size, and they have a wide range of compatibility, especially being able to adjust the length of that carbon chain between the two ester groups. You can usually customize your compatibility pretty well. Aromatics, on the other hand, especially phthalates, were low cost, but some of the others can also be fairly low in cost. They give a good balance of properties. They may not necessarily be the best at low temperature flexibility or the best in one particular property, but they can give you a good balance across the board of good everything rather than excellent at one and really sacrificing in one other area. And the other nice thing about aromatics is that you can blend them very well with higher performing esters. You might find an ester that solves all of your problems and does everything incredibly well because it's such a high performing material, but it's too expensive to actually be used practically. A lot of times aromatics can be used to kind of blend with those that give good compatibility and help to not dilute down the performance too well. So those were the different acids. What can we do with alcohols when we're reacting with those acids to give these ester groups? The first thing that we can look at is carbon chain length. This is similar to the acids, but we can adjust the length of our chains coming off of the ester groups in the middle. A longer chain, such as in the DIDA, the diisodecyl adipate there, will give you an increased carbon to oxygen ratio, as we already discussed, decreasing your polarity. You'll get reduced volatility, being a larger molecule, better low temperature flexibility, but you'll often see poorer processability because it's such a large molecule compared to their smaller counterparts. With a shorter chain, like diisobutyl, which has a very short carbon chain coming off of the ester groups, you'll see an increased volatility since it's much smaller, worse low temperature than with the larger material, but you'll see an improved processability. The smaller molecule is able to move more freely. And the other thing to consider is branching. Branching can give some interesting effects on your material when you're processing. The examples shown here, technically on top is dioctyl adipate, which is actually not DOA, which most people see. Most people say DOA and say dioctyl, but what they really mean is this di-2-ethylhexyl adipate. 2-ethylhexyl alcohol is much less expensive than just octyl alcohol, the straight chain, so it's much more commonly used, but instead of using the full name with the 2EH there, a lot of people say DO instead. But just to give an illustration here, these two materials are the same molecular weight, have the same chemical backbone as far as carbons to oxygen ratios, but the top material has no branching, the bottom has some short branches coming off the side, just to illustrate what I mean by branching. When you increase branching but maintain the same molecular weight, you tend to see increased volatility. The way that the molecule is arranged increases the volatility when you have branches coming off of it. You'll see worse low temperature flexibility. The reason behind this is if you think of your polymer matrix as an entanglement of long chains, the more branches you have on your plasticizer, the less freely that plasticizer will be able to move between the chains because those branches get more entangled. That allows for less overall mobility, giving you worse low temperature flexibility than with a simple straight chain. You'll also see poorer oxidative stability. There's more sites in the molecule that are ready to be oxidated. So you'll see worse stability in that area. But what it does for you is it helps to increase your migration resistance. Like I said, with the material being entangled in the polymer matrix, you won't see as much migration because your plasticizer won't be able to move as freely. So it's more likely to stay in your compound over time. So we're going to take a short little break here because this is a course, and just do a quick little learning evaluation in Heather. I don't remember, should it be in the chat or in the Q&A function? In Zoom. Sorry, if you can, I think it's in the Q&A. But if you can kind of hop in here and answer the question that we have, we got the chat. Okay, we have the chat over here. So what is the single most important factor when we're selecting a plasticizer for your application? I'll give you a minute to answer. So yes, I'll just jump back in here. It is compatibility. That if there's one thing that you can take away from this course today, it's that you need to consider compatibility before anything else. Because if you just look at numbers and data and say, oh, this will be great, this will soften my material, and then you get it and it's not compatible, then it's obviously not going to work. And then next, we have a nice little multiple choice one here. So this will be a little easier to type into the chat window. But which of the following can be used to predict your compatibility between your formulation and a potential plasticizer? And it's a select all that apply. Oh, it looks like Heather is asking if we can put our answers in the Q&A, not in the chat. I apologize for that. I couldn't remember what she had said. So yes, what we're mostly looking at here is polarity, number one. That's kind of the quickest and easiest way to predict compatibility, and solubility parameters. Those are kind of some of the biggest tools. Viscosity that's more when you're looking at mixing. Sometimes if your viscosity is maybe too high, or there's an adjustment between the plasticizer and the polymer, it can more have to do with the initial compounding and getting the two materials to come together. But typically viscosity doesn't have too much of an effect on the overall compatibility between the two. And then refractive index, I was mostly just looking at other material or other things that we measure when we're doing plasticizers, and that really has nothing to do with compatibility. That's more about the light coming through the plasticizer. So moving on, now we've talked about kind of the chemistry and how we can make up plasticizers using various acids and alcohols. Let's talk about the plasticizers that are available and the different types that are out there. There's two main groups. There's monomerics that are single molecules, tend to be essentially identical molecules throughout the material. And they are very small and usually very free moving. And there are polymerics that are long chains of repeating units, kind of a similar idea if you think about your plastics and your rubbers, just with esters, and typically much lower molecular weight because they are almost always liquids. Breaking those down even further, within monomerics, there's three main types. There's monoesters, which are not quite as common. They are used fairly widely, but not as widely as the other two types of monomerics that I'll talk about here. Monoesters typically have excellent efficiency. They are fairly small, and with only one ester group in the chain there, are very good at softening even at lower loading levels. They also are typically used mostly in low polarity applications because they only have that one ester group. They're going to be more compatible with your low polarity elastomers. Diesters are probably the most common, the most widely used monomeric esters out there. They have 2 ester groups, as you can see here. These are things like your DOA, your DOZ, your DOS. Essentially, any plasticizer where you see a D in front of it is almost always a diester because that D usually means di. Diesters give excellent, excellent low temperature properties most of the time. Triesters are also still fairly widely used. The one shown here is TOTM, trioctyl trimeltate. These have 3 ester groups coming off of a central, usually aromatic ring for something like a trimeltate. They offer excellent high temperature performance, especially for a monomeric, which typically aren't as strong in high temperature applications. Triesters really do a good job in that area. Polymerics, polyesters can vary so widely that it's really difficult to group them into any further groups. So we really just leave them as just polymerics, polyesters. And what they mostly offer is excellent extraction and migration resistance because they are so large. So why would you choose one over the other? We'll talk about monomeric esters first. Monomeric esters provide excellent low temperature performance because they are such small molecules. They can move very freely and they can offer excellent flexibility. For the same reason, they have excellent plasticizing efficiency. You usually don't need to use them at very high loading levels to get to really see an effect and to see benefits. They're really well suited for more commodity elastomers, things like NBR, chloroprenes, and then even PVC blends with elastomers as well. Monoesters do very well, or monomeric esters do very well there. Just a really nice, easy pictorial show here of how we make these esters. On the top line is a monoester. We just use a monofunctional acid that has 1 acid group, a monofunctional alcohol with 1 alcohol group. They react together to form 1 ester group with the acid and alcohol chains coming off of the sides. On the bottom, to make a diester, something like DOZ, DOA, DOP, we have a difunctional acid that has 2 acid groups, 1 on each end of the molecule, and we use 2 monofunctional alcohols, similar to in the monoester, and each one reacts with 1 of the acid groups to give a diester with 2 ester groups. Polymeric esters, on the other hand, give very low volatility because they are such large molecules in comparison to the monomeric esters. They have excellent extraction resistance to a wide variety of fluids because they are so large. They don't move as freely. And these are really especially suited for higher performing applications and elastomers. So similar to the monomerics, but also things like HNBR, polyacrylates, just the higher performing materials. And then on the right side here, just to illustrate, because we have these nice repeating units, it gives us the freedom to terminate that polymer in an acid group. We can terminate in an alcohol group, or we can even leave the polymer chain unterminated to give that hydroxyl group on the end. And by having different end groups, we can impart different properties and different interactions with the final polymer. So same pictorial illustration here. Similar to the diester, we use a diacid, but we also use a difunctional glycol so that we have the ability to make a nice long chain that they keep reacting with each other every other unit. We have an acid, then an alcohol, then an acid, then an alcohol, grouping together to give ester groups. Every one of those black lines is 1 ester group between each molecule to form 1 long molecule. On the right side here, it just shows with an alcohol, but this can also be done with the acid, that we can mostly have diacids and dialcohols or glycols, but we can also add a small amount of monofunctional alcohols to kind of cap that chain and stop it from reacting any further. And that gives us unique properties for the chemistry of the end caps of the chain, but it also helps us to control how long those polymer chains are by adding a certain number of those monoalcohols to not allow them to get any bigger. On the other side, we can not add those and allow the chains to just get as big as possible to really raise up that molecular weight, which can be really useful in certain applications. So there's a lot of data on this slide, but I'm going to draw your attention to a few things. This is more so that if you want to look back at this later, you can look at the numbers a little bit more closely. This is to show within chemistry families, so adipates, sebacates, and acylates, the difference between a simple monomeric of that chemistry and then a polymeric version of that same chemistry. The first thing that is very clear of the difference between the two is overall tensile strength. Polymerics are going to not be as efficient at the same loading level as a monomeric would. So you see a lower tensile strength with the same loading level of a monomeric versus a polymeric within the same chemistry family. The next thing though is the low temperature. As I talked about before, the monomerics are much better at low temperature than polymerics, and that's very, very clear here with both brittle point and a Gaiman measurement. The monomerics have much better low temperature performance than the polymerics of the same chemistry. But on the other side, looking at high temperature, this is an air oven aging, I believe this one is at 125 C. The weight change is significantly better in a polymeric versus a monomeric because the monomerics are much more volatile and are much more likely to evaporate off of your material and come out, leaving you with a more brittle material after heat aging than if you had a polymeric present. And the same thing looking at in solvents. This is that extraction resistance that we talked about. Just kind of overall looking at the numbers, you can see that on the left side of each column, you see much higher extractions coming out, much higher weight changes versus the polymerics on the right side, which you don't see as high of weight change really in anything in the higher polarity or in the lower polarity materials, oils, waters, things like that. So just to kind of sum up the benefits of one versus the other, but again, there's always a range within monomerics and polymerics. So this was meant to just kind of be an overall summary. In processing, you tend to see better processing in monomerics than in polymerics. That doesn't mean you can't get good processing out of a polymeric. It just depends on the molecular weight, the structure, what your final loading level is. There's lots of things that could affect this. But overall, you tend to see better in monomerics. Compatibility we include here to highlight that monomeric versus polymeric has almost nothing to do with the compatibility between your ester and your polymer. That is almost entirely dependent on the chemical structures that are being used. You might see a slight difference just because polymerics are so large, they're less likely to move, but overall, you're not really going to see very much of an effect on your compatibility on one versus the other. For softening efficiency, again, this is similar to processing. It tends to be better for monomeric, but if you have a low molecular weight polymeric, you can still get some good softening efficiency out of it. Low temperature flexibility, as we saw in the previous slide, is almost always going to be much better with a monomeric versus a polymeric. And then extraction resistances. This one can also depend on the chemical structure as we talked about with adjusting the polarity. You might see better in an aqueous or an organic based on your polarity, but overall you tend to see better extraction resistance out of a polymeric than a monomeric. And then with volatility and migration, absolutely, polymerics are almost always much better than monomerics just because they are such large molecules. So just to delve a little bit further, because we talked about the low temperature versus the high temperature performance of monomerics and polymerics, I just want to talk a little bit more because this is such a kind of a hot subject when people are talking about plasticizers. A lot of times people are using plasticizers to improve their low temperature performance. Or they're using plasticizers in high temperature applications and they need something that can withstand those high temperatures. So I'm going to talk about both right now, starting with the low temperature esters. So for something that is primarily designed for low temperature flexibility, you're talking about something that's going to be a small monomeric molecule on average. They're going to be extremely efficient at plasticizing, so usually not as much is needed to give good properties, and you'll see excellent processing because they provide that excellent excellent flexibility. But on the other side, you see a lot of high volatility in these materials because they're so small, and they're much more likely to migrate or to be extracted out of your material. Just some common low temperature esters that are used very regularly, so the chemistry is listed on the left of exactly what the material is, and then the common abbreviation on the right used by both Hallstar and other companies that are making these materials. These are the abbreviations that you'll see with these respective chemistries. Mostly diesters, as you can see. We talked about earlier that diesters tend to give some of the best low temperature flexibility. There is one triester in there that's a little bit unique, but most of the others are diesters, as we've seen improvements before. Just to show the difference though between those, that's a nice list of low temperature esters, but even within them, some are better than others depending on your application. This was in an NBR compound with a medium ACN content of 33%, 20 parts loading of plasticizer, about 10% total of the compound. Just to compare directly, so in the first two columns, you'll see the diisodecyl adipate versus the dibutoxyethoxy. The average molecular weight is very, very similar. It's not exactly the same, but it's very close. However, in the diisodecyl, we have a nice long carbon chain, whereas in the dibutoxyethoxy, that has 2 extra oxygens in addition to the oxygens that are in the ester groups. So you have a severe increase in polarity in the DBEEA versus the DIDA. So even with this about the same molecular weight, you see much better low temperature in the more polar material here than in the less polar, both by TG and by brittle point. And following on the same kind of trend here with the 4141, that was the one triester in the previous slide. That also has a similar molecular weight to the first two, but it's much more similar to the polar material, just showing that it's a triester versus a diester. You can adjust your low temperature flexibility there. And then the final column has a much lower molecular weight material, almost 100 less than the others. And you can see that the molecular weight has a great effect by reducing even more those low temperature properties. So let's switch to high temperature esters here. For high temperature esters, you're looking for something with extremely low volatility, because usually with this, you want something that is not going to volatilize out at those high temperatures, that's going to stay in the compound and continue to work even after being exposed to high temperatures. Usually when you have that kind of a situation, you also improve your non-migration compared to common monomerics because they tend to be much larger molecules. And they also will have extraction resistance to a wide variety of solutions, but often to aqueous solutions. On the other side, again, you have your cons that they tend to be much more difficult to process, being larger molecules, and they're less efficient. So usually a higher loading is needed to get the same softening efficiency as a lower molecular weight material. Common high temperature esters, typically, if you really want something high temperature, you're going to be looking at something polymeric. However, there are some monomeric materials if you're looking for something that's a little bit more of a balance, or if there is some reason that you really need to be using a monomeric versus a polymeric. Trimelatates tend to be the best, with TOTM being the most common high temperature monomeric ester. But really, if high temperature performance is the most important thing, polymerics are going to be the best bet. This is just 2 examples of proprietary chemistries that Hallstar has. The A8600 is an adipate and the G25 is a sebacate, that are 2 of the highest molecular weight polymeric esters on the market, I believe, but definitely within our profile. So we'll do another one of these quick little learning evaluations to kind of sum up everything that we talked about with the monomerics, the polymerics, high and low temperature, things like that. So we'll go back into the Q&A and select all that apply of these choices here, and which of them are the best performance benefits that you would receive from a monomeric plasticizer. Yes, so first definitely would be efficiency. Monomerics are extremely efficient because of their small size, and low temperature is really one of the best ones. And then on the other side, which of these would be best with a polymeric plasticizer? Okay, yes, definitely migration and extraction resistance is always better with a polymer, and that low volatility in high temperatures. I included the compatibility here just to highlight one more time that monomeric versus polymeric is usually almost not affected at all by compatibility, or does not affect compatibility very much at all. Hold on. There we go. So just to kind of sum up what we just talked about in that learning evaluation, but to help show monomeric versus polymeric and just in general ester chemistry solutions that can be provided for common concerns. On the left side in that compound property, we have different properties that are often a major concern when selecting a plasticizer for different applications. And in the middle, we have our ester chemistry solution of how we solve those problems or how we address those issues, and then some example products, both monomeric and polymeric typically, that could be used in each of these situations. So first, for low temperature, mostly monomeric, but overall you can also use long linear carbon chains and just an overall low molecular weight. So the diesters, as we've talked about, but also low molecular weight polymerics can still give very good low temperature flexibility if you need a balance between that and some other property. Low volatility when exposed to heat. We can use that high molecular weight, but another thing that I didn't really mention too much about when we were talking about raw materials, but it's something that we can do when we're synthesizing, is if we look at raw materials that have high boiling points to start with, that typically results in a higher boiling point ester and a lower volatility ester in the end. So typically monomerics, you're looking at things like TOTM, but really just large molecular weight polymerics are the best when looking at low volatility. For extraction resistance, this one can depend a lot on the chemical structure because it depends on what fluid you're talking about. If you're talking about something that's extremely low in polarity, like oils, then you need to make sure that you're going with a higher polarity material. So maybe something with ethoxy functionality and extra oxygens put in there, or shorter carbon chains between the ester groups. Overall, higher molecular weight is always going to be better. But then on the other side, if you need something that's going to be exposed to high polarity things like water or automotive coolants, say, you need to make sure that you're going with a lower polarity, usually polymeric material. And that can kind of affect what it is that you're talking about. You need to make sure you focus on which fluids you're looking at. And then finally, migration resistance. This is not when you're talking about something in contact with a fluid. It's more just the part sitting on its own, whether the plasticizer migrates out of the compound, either to the surface, or if it's in contact with another solid substrate, like another polymer. You want to make sure that your plasticizer is not migrating out of your original part. So usually high molecular weight and the branching can help a lot with the migration resistance. So I'm going to talk a little bit through a few case studies just to give you an idea of some common problems that we've seen in the past and how esters have been able to solve these problems and how we were able to approach all of these. This is a very simple, straightforward application here. It was an NBR printing roller, something that was transporting ink. They needed improved solvent extraction resistance from both the solvents in the ink, but also solvents that were being used to clean the rollers. They were having problems with the plasticizers extracting out over time and reducing the softening in these print rollers and making them much harder and more brittle and not performing up to their standards. And using our Paraplex approach that Dani mentioned earlier in the material, we were able to use that DOE and help to optimize a product that both improved their solvent extraction resistance by 10% over the existing product that they were using, and it also ended up reducing the cost of their product by taking that into account as part of the DOE. That's something that can be added. This is something that we love just because it very clearly shows with a real world application the benefits of a polymeric versus a monomeric when you're looking at migration. So this is what I mentioned before about migration not being extraction. These are high voltage cables that were just in the environment you see here, nothing with any kind of fluids extracting the material out, anything like that. Just with high use, these materials, the monomeric plasticizer that they were using was just migrating out and gumming up their parts horribly. And they needed a solution to this. Just by replacing a monomeric with a polymeric, even a simple polymeric, it wasn't even anything really that complicated, completely eliminated their problem. There was no migration whatsoever. And so you can just very clearly see, we talk about polymerics being better for migration, but in these pictures you can see it. Next was an HNBR powertrain belt. So this is like a really high performing part, something that's going to be exposed to 140 C at operating temperatures. It needed to have good oil resistance being under the hood, but it also needed to maintain good low temperature flexibility all the way down to -40. Automotive applications are tough in this regard, especially under the hood, because engines will run very hot, but then you also need to make sure that your car is starting in the middle of winter in the Midwest. Why they were looking at an ester plasticizer to help solve their problem in this is that esters can often perform very well retaining low temperature performance even after being exposed to heat, which is what's most commonly needed in these kinds of applications. And that the parts, because this is a powertrain belt, it needs to stay flexible for 100 to 150,000 miles. They don't want people to be frustrated having to replace these more often than that. The solution given here was a high molecular weight, polar monomeric ester. With it being polar and monomeric, we got some very good low temperature flexibility, but by increasing the molecular weight and making it a very large molecule, it helped to withstand those high temperatures and stay in the compound much better than if it was a very simple low molecular weight monomeric. It's giving that excellent flexibility and low temperature even after the heat aging, and it can also be used at fairly low levels. Because it's monomeric, it was more efficient than a polymeric would be to achieve those physical properties. EPDM is always an interesting one because most people typically do not use esters in EPDM, but this was a unique application. This was an EPDM seal that was being used in downhole drilling. The first thing that we asked is why were they using EPDM instead of a higher performing elastomer like NBR or HNBR? In this, they needed something that could maintain flexibility and with no cracks. It needed to swell in water and kerosene and not shrink because of plasticizer extraction. They were using a peroxide cure system to help improve the performance overall of the part versus a sulfur cure. And the reason they were looking at an ester for EPDM, where EPDM, for anyone who might not be as familiar, typically uses process oils as a plasticizer because they are extremely compatible in EPDM, being very, very low in polarity. But they're also very inexpensive, especially compared to an ester plasticizer. EPDM in this application, though, typically swells for their water displacement, but in this, they also needed something that would retain at least some level of oil resistance. And process oils obviously will not be very resistant to oil because they're very, very similar in their chemical structure. So they wanted an ester to help offset that. This was a difficult application to find a solution for, but we were actually able to offer them a reactive plasticizer, something that has some unsaturation in the backbone of the plasticizer. Now, this was only effective because of the fact that they were using a peroxide cure system. These types of plasticizers have not been shown to be very reactive in sulfur cure, but in peroxide cure, the peroxide can actually cross-link the plasticizer into the polymer network, just giving an even better resistance to any kind of extraction or migration because they've been chemically bonded to the actual elastomer. And so it was not extracting out, it was not migrating because of incompatibility, because everything was bonded together, and it was able to give them the needed swelling from the water, but still have resistance to the oil in the end. And then just one quick last thing here, looking at acrylics, because that's another common application for a lot of esters. A lot of times acrylics don't like to use very much plasticizer, and that's understandable because they tend to be very high performing and they don't want to sacrifice any of that performance by diluting with a plasticizer. But in this case, we're looking at a control with no plasticizer whatsoever versus the Tegmer mentioned here. That's the same material I mentioned with the HNBR. That was the high polarity, high molecular weight, but still monomeric material versus a typical, fairly standard, relatively low molecular weight polymeric material. Both of them showed some additional weight loss, as would be expected by adding them in both the post-cure and after a week at 175 C, but not a significant amount. We saw slightly more with the monomeric versus the polymeric, as would be expected, but again, not significantly more. But where we really saw the benefit here was in low temperature. The monomeric that we had mentioned before gave excellent initial low temperature, but also gave much better low temperature than even the initial low temp of the polymeric material. We didn't lose very much performance even after aging at a fairly high temperature in this acrylic. So it just shows how kind of that high polarity, high molecular weight monomeric can give a good balance between the two properties. So just to kind of sum up, we have a long history in plasticizers, especially in ester and especially in the elastomer market. We have a wide range of experience in what we've worked with in the past and what we've been able to solve problems. We have combined decades of experience and over 100 different monomeric and polymeric products, a very wide range, and we love to help our customers. I really hope that this course helped to give you a lot more knowledge moving forward with being able to select plasticizers yourself and being more knowledgeable about looking at the market and seeing what's available and what would work best in your application. But if you need further help, we love to help people with this kind of thing and to help educate you even more. And here's our contact information. And then I believe Dani was going to handle any questions. You can type them in the Q&A there.
Yeah, so why don't I just start by reading some of the questions that have popped up, and Erica will offer some answers to these questions. So we have 3 so far, and yeah, again, we encourage you all to type any and all questions into the Q&A box. But our first question is, what do you think is the reason that polymeric has better tensile than monomeric?
So it depends on what you mean by better, because sometimes better can mean higher. Some people want a lower tensile strength. It depends on the application. But typically, polymerics have less efficiency than monomerics when softening and when reducing things like tensile strength or modulus and increasing elongation. So at equal loading levels, polymerics just aren't as efficient, so they won't soften the material as much. They won't cause it to break earlier than with a monomeric, which makes the material a lot softer typically.
All right, our next question. Do you have any applications of these esters in natural rubber, styrene butadiene rubber, or polybutadiene rubber?
We do have some because esters tend to be, as we showed with the polarity chart earlier, esters typically are used in the more polar elastomers, so that's what a lot of our literature is geared toward. But we do have a history. We actually especially did some work in tires, primarily looking at SBR and butadiene rubber. That's what our Star Tread line is based on, if you look at any of that literature. And so we have done work specifically in that area. We've done some in natural rubber, but that tends to be more on a case by case that we address those issues as customers bring them to us. We don't have kind of our full portfolio in those rubbers because we haven't seen as much of an application there. But that's something that we can absolutely address if you had specific questions.
All right, next question. Do you specify alcohol group amount in the esters? Because OH is the root cause for mold fouling, according to my investigations.
Can you read that one more time? Sorry.
Yeah. Do you specify alcohol group amount in the esters? because OH is the root cause for mold fouling, according to my investigation.
So for some esters, yes, we do. One thing I didn't really talk about today, just because it was a 1-hour webinar and I didn't want to delve too deep into this, but the QC properties that we typically report, we always report acid values, but for many, we also report OH values and hydroxyl groups that are present. So that's something that we definitely look at, and especially if it's something that's important, we can always easily measure those, and we can specify them. It's, I believe off the top of my head, it's not a standard for every ester we have in-house, but it's something we can easily test if it's a product you're interested in that doesn't already have it reported.
All right, next question. Is any plasticizer available to reduce the anti-static properties in the rubber compound NR, BR, or SBR?
That's something that we've actually been looking at a little bit more recently, is things like electrical properties. That's not something that we had historically done with all of our products, but we've been getting more interest in that more recently. So that's definitely something we have been looking at. We've been measuring things like resistivity and dielectric constants and things like that of just our neat products. I don't believe we have any data on that in those compounded rubbers. But again, that's something that we could definitely address as we've been moving towards it.
All right, next question. Are all ester plasticizers fully saturated? I noticed a vegetable oil with some unsats had good retention, I believe because it participated in cross-linking.
Yes, so that's something in the EPDM case study that I mentioned. Most are fully saturated just because of the nature of raw materials. A lot of times, most people want them to be saturated. They don't want the unsaturation present. But we do have, at least that reactive plasticizer is definitely unsaturated. And then we have some that are oil-based and fatty acid-based that have some unsaturation. And that's actually something that I'm currently working on, is testing some more that we are hoping to be reactive. I was weighing up ingredients this morning, actually, to be testing some more of these. And we know that that's something that's of interest, is having some level of kind of reactivity, especially in a peroxide cure system, because those tend to be easier to react. So we have a few available. They tend to be more specialized, so we don't have as wide of a range, but there are some that have some levels of unsaturation.
All right. Any data on modifying tan delta at 60C rolling resistance and 0C wet traction in tire tread rubber?
Yeah, as I mentioned a little bit when talking about that question with SBR and the BR, we have done a lot of work in the past, both before I was with the company and then after I joined, testing in tire compounds. Mostly we used a formulation from a Michelin patent that used SBR and BR, and we did some DMA data on those with few different esters. I don't remember how many we have that are considered our star tread products, but we have data on those that I believe we have in the literature section of our website. I think that we have our star tread presentation in there that has a lot of that data reported, and if not, that's something that if you contact me, I'm sure I could give you a lot more information on that.
Is ESO considered a reactive plasticizer? If so, how does the extraction resistance compare with your reactive plasticizers shown in your presentation?
So ESO, we haven't seen as much application or use for in rubber. It's typically used in PVC as more of a stabilizer. We don't usually consider that to be a reactive plasticizer, and to my knowledge, we don't have anything directly comparing it to that reactive one that we have. I could dig back through our data, but as far as I know, we have not compared those directly. One of the things I know we mentioned earlier about how some of our new work has been in looking at bio-based and more sustainable materials, and we are actually looking at more things that are based on that soybean oil, not just ESOs. So that's something that we're also considering and that we're working on.
All right. Could you elaborate a little further on the difference between primary and secondary plasticizers and how that contributes to compatibility with crystallinity?
So the primary and secondary, that's more on the theory side of things, and it's difficult to really differentiate that well between them now because that's not a concept that's as widely used. It's hard to talk about that one just because people don't really talk about plasticizers as much as being primary versus secondary. We mostly just look at every time we compound something, we look at what it does in different elastomer systems. We things like EPDM that you have to worry about crystallinity and things like that. That's the only times that we're really looking at those kind of things, and we are more considering whether our plasticizer has any degree of crystallinity and how that interacts with the crystallinity in the EPDM. And so that one's a little bit harder to elaborate on. That one might be better talked about offline, I think. If you want to contact us directly, I'm sure we could talk about that one a little further.
How resistant are ester plasticizers to microorganism or bacterial attack?
So typically we don't really see too much of a problem with this. That's not something that I know that we've tested specifically, but as far as I know, that's not really an issue that any of our customers have ever reported seeing. The only time that we did have a slight issue with this was we were working with someone recently about making water-soluble materials. And obviously something like water, moisture tends to grow things like microbial issues and things like that. So we did have a slight issue with that, but usually if you add an antimicrobial agent, you can kind of help to mitigate that problem. But just ester plasticizers on their own, I don't know if we've ever tested it with data, but I don't think that that's ever really been a significant issue.
Do esters fare better than petroleum-based oils for UV and ozone performance in natural rubber?
In natural rubber, I'm not sure specifically, but I believe that they typically do. Again, it depends on the ester. It depends on the raw materials that are used initially that you see, and so I think typically though they do perform a bit better.
Any issues with peroxide cure with the aromatic esters, since the aromatics tend to use up some of the free radical cross-linking reagents?
That's definitely something that can have an effect. I know that that's something, especially when you're talking about like petroleum oils that have aromatic content, that can be an issue. So using an aromatic plasticizer can definitely have an effect on that as well, or an aromatic ester, I should say. You can see that the peroxide attacks the aromatics first. So typically, like with our reactive ester, when we mention that, that does not have aromatic content. It has unsaturation so that it can react into the polymer network, but it does not have any aromatic content so that you don't have to worry about that side of things. But it is something to consider. Thankfully, usually you don't see those used as widely in peroxide cures, and they're not as widely used anyway. Typically, you're seeing aliphatics more often used in those.
Okay, do we have any more questions? Give everyone like 30 seconds.
Mm-hmm.
Type into the Q&A box if you think of anything.
While we're waiting for that, I just want to thank you both, Dani and Erica and Hallstar, for putting on this great webinar. Just to remind everyone, we have opened up all of our webinars at Rubber Division free to our members. Please check our Rubber Division or rubber.org/upcoming training for our webinars being offered this summer. We will also be adding new courses in the next few weeks, so be sure to continue to check our schedule of events so that you could attend one of our upcoming courses. We also have opened up these courses free to student members for the upcoming year as well. So thank you again for joining, and I've emailed everyone the handouts as well as the survey, so please feel free to email me if you have any other questions, and we can get you in touch with Hallstar if you did not take down their information. And just thank you again, everyone, for joining. Have a great day.
Thank you so much.